He's working on a physics degree, comp sci minor?
No, major.
Major? Physics and comp sci, okay, double major. And this, so perfect example of someone who is a biophysics graduate student to be, I would say.
Okay.
In the summer, he was working with Brian Coleman. So tell us about that.
Hello, everyone. Once again, my name is Xavier Bonner. I'm a physics and computer science major from Cleveland, Ohio. Over the summer, I worked in Dr. Brian Coleman's lab, dealing with the analysis of relative binding affinity for protein-protein complexes. So why are proteins important and the complexes they form important? Well, essentially, if you can elucidate when and where and under what conditions these proteins like to bind together, you can begin to design network maps and better therapeutics that bind strongly to these structures. So things like bone cell synthesis, red blood cell production, neurotransmitters that control your mood are all functions that are mediated by proteins. So one thing that scientists are particularly interested about are the energetics, how we understand these energetics and how we begin to model these energetics of protein structures. So that is a way to mathematically model these binding energies is with this binding energy equation. So in order to calculate the binding energy of a protein-protein complex, we take the Gibbs-free energy of when the protein's in this complex state, and then we subtract that from the constituent partners that constitute the binding energy, that constitute the complex, rather. So to mathematically calculate the relative binding energy, say if we introduced a mutation to the binding site between these protein interactions, we would take the binding energy of the mutant and we would subtract that from the binding energy of the wild type. So one great tool that is used to model these macromolecular interactions is Rosetta, which is a multi-purpose platform for designing macromolecular structures, and also it is commonly used to model these, model and understand treatments of infectious diseases. What I'm interested in is seeing how these protein structures are able to be modeled and the energy levels that we're able to produce with this software. So that brings me to the specific aims and goals of my project over the summer. So the overarching goal was to identify how precise Rosetta protocols are at predicting binding affinities for protein-protein complexes. Within this overarching goal, I had two aims. First aim was to find which Rosetta protocol best predicts the relative binding energy when a mutation is introduced to the interface. The second aim was to elucidate whether structures should be simulated when they're in this this complex state and then separated, or when is it best to simulate when we just separate them all about and run simulations on these structures. So in order to understand that concept, I threw a quick animation to help you get that. So the first experiment is like when we have it in this complex state, we do the simulation and then we separate the structures all about. Then we would address and calculate the relative binding energy of the partners. Now that is different in the sense of this experiment where we just separate the structures first and then run simulations upon the structures. So, to describe the data set that I use to run these huge simulations, we have a data file of about 3,900 single and multiple point mutations. And across this data file, it encompasses about 190 protein structures, so a vast library. additionally, we have about half of the mutations are single point mutations. When I say that, I mean that one residue structure within the complex between the interface is going to be mutated. For multiple point mutations, that means that multiple amino acids between this interface are being mutated. Another important note about this data set is that multiple protein domains constitute the interface. So you can have not just two partners that make a complex, but you can have 5, 6, or even up to 15 points. So some data metrics that I used to interpret the data was this root mean square error. So within, from the data set, we have the actual predicted relative binding energies of what the actual relative binding energies of the mutations that we're putting into the protein structure. So we can compare that to the predicted value that we're using, that Rosetta predicts. So when we do that mathematically, we have, again, the reference point of the actual DDG value, and we subtract that from the predicted DDG value. We square that, and we find the average of the entire predicted data set. Once we find the average of that, we take the square root, and that gives you the root mean square error. Another data metric we use to interpret this data is the Pearson correlation, and that number that tells us how well the predicted data set did against the actual data set. So if this number is higher, that's good. So just to give you a sense of the pipeline I did to simulate these huge structures, the first step in this protocol is we have, say we have a protein structure that has 7 or 8 different protein domains that constitute the entire structure. Well, we don't really need the entire protein structure to simulate we don't need the entire protein structure to simulate what we see when we introduce a mutation between the interface. So we essentially strip away all the excess protein domains, and we're just left with what is relevant to our interactions. So the second step in this protocol, we then adapt the protein structure to be able to run these Rosetta simulations, and finally we introduce the mutation between the complexes. We then calculate the relative binding energy, and then we analyze the correlation between the predicted data set and the experimental data set. So one of the first protocols that we ran was this protocol called variable relax. And the steps included in this protocol is we first store an internal representation of the structure in Rosetta. Then we either separate if we're simulating the complex state or the separated state, we either separate the components that constitute the complex, or we just keep it bound together. From there, we then add coordinate constraints, then we repack the side chains, and finally, we minimize the degrees of freedom. So I'll just preface the next 4 slides with this statement. So you want to look at this teal line and see how well dispersed, or how close, rather, the points around that teal line are to the teal line. So if those points are close to that line, that's a good predicted value. If they're farther away, those are what are called outliers. And again, if these if these points lie above this teal line, those are what are called over-predictions. The points below this teal line are what are called under-predictions. So when we ran this variable relax protocol, we found that the Pearson correlation for all point mutations was around 0.4, which is a relatively okay Pearson correlation. So when we broke it down a little bit further, we wanted to see how single point mutations did compared to multiple point mutations. And we found that the single point mutations weren't predicted as well as the multiple point mutations were. So rolling with this variable relaxed protocol, we introduced what are called distance constraints to the protocol. And that essentially doesn't allow atom pairs that are near the mutation to move a certain distance away or closer to the mutation. So when we did that, we saw that our experiment vastly dropped in terms of Pearson correlation compared to what we had previously tried with just variable relaxed. We saw a Pearson correlation of about 0.02, which is a pretty bad Pearson correlation. But when we looked at single point mutations compared to multiple point mutations, we saw that single point mutations did not score very well, and multiple point mutations scored pretty good compared to the overall structure. So I was interested to see why these structures were scored so poorly, and when I looked at the wild type compared to the mutant, I saw that there was a lot of intermolecular clashing outside the distance constraint range. And one possible effect that caused that was that a picture like a sphere, and inside that sphere you have all the residue structures that are constrained. Well, outside that sphere that is unconstrained, if those residue structures are pulled towards or away the mutation, that's obviously going to affect the outside structure. So we also simulated the variable relaxed protocol with this docking step. And when we did that, we saw that compared to the distance constraints run, that did vastly better. We saw for all point mutations, we had a Pearson correlation of about 0.38, and for all point mutations. And when we looked at single point mutations compared to multiple point mutations, they were really closely correlated together. So this protocol was better than the variable distance constraints run. As an overall trend for this run, we also saw that there were about 29 over-predictions for the entire data set, whereas there were about 303 under-predictions. So it under-predicted at a higher rate than over-predicted for all point mutations. So another protocol we ran on these structures was this repacking experiment. And what that does, basically, it repacks the side chains at a different step. So we saw that there was a large amount of variance compared to just the variable relaxed protocol. As you can see all these points that lie further and further away from that teal line. While this is better than the variable relaxed with distance constraints run, it still didn't accurately predict these delta G points. Again, when we looked at the single point mutations compared to multiple point mutations, we saw that a Pearson correlation was relatively the same, and we also saw that the margin of error was relatively the same. So the last protocol we ran on these structures was this relaxed protocol. And we found that this was the best protocol for our data set that we ran. We found that there is a Pearson correlation of about 0.418. So that's, again, the best Pearson correlation that we had tested. Or that's the best Pearson correlation that we found. And when we broke it down again between single point mutations and multiple point mutations, we found that multiple point mutations outscored single point mutations. So the second aim, again, as I stated earlier, was should we separate the structures before we simulate them or after we simulate them? And what we found was when we separate the structures, while they were in this compound state, then we found that there was a better Pearson correlation than when we didn't separate the structures. So it's not a huge difference between the protocols, but you can see that there is more outliers when we didn't. So we weren't completely convinced, however, so we used the variable relaxed protocol, which is also had a decent Pearson correlation overall. And we found that, again, the same trend did occur when we simulated the protein structure when it was in this complex state and separated it after. So again, this protocol worked best. So to conclude, we found 4 overall trends. We found first that Rosetta underpredicted at a higher rate than it overpredicted for the protocols that we tested on the data set. We also found that in most cases, the Rosetta protocols we used better predicted multiple point mutations compared to single point mutations. We also found that you have to simulate the separation when it's in this complex form, and then evaluate the energy, and instead of just separating them and then doing simulations on them after. Finally, we found that the best protocol to run with this specific data set was this relaxed protocol. So in the future, I would like to change the score function to see how the different weights affect the overall simulations of this data set. And I also want to identify specific protein structures that reoccur as outliers. Like, why are those outliers? Why do they confound the data set that we're using on the protocols that we're using? Lastly, I want to find an efficient and precise way to automate this trimming protocol, or this trimming method, because there can be a different way where we can just trim essentially certain distances away from the interface instead of just stripping away excess chains. So I would like to thank the Biophysics Summer Program, Dr. Mike Jarsfa, also Lisa, she did a great job with coordinating everything for our program, Dr. Coleman, my postdoc, Heretin, also the entire Coleman Lab, the Biophysics Society, and also the National Institutes of Health for funding this